Okay, this is David Zierler, Director of the Caltech Heritage Project. It's Friday, September 2nd, 2022. I'm very happy to be here with Professor Timothy I. Melbourne. Tim, it's great to be with you. Thank you for joining me today.
My pleasure.
Tim, to start, would you please tell me your title and institutional affiliation?
Yeah, so I'm a professor of geophysics at Central Washington University. And I went there straight from Caltech, and I've never left.
Tell me about geophysics, seismology, geology at CWU. How long has the program been in existence?
The geological sciences major, I think, has been around for a very long time, probably 1920s to 1930s. And the way I ended up there is directly attributable to my experience at Caltech. So I came of age. I got my PhD right around the time GPS geodesy was getting quite mature and had kind of reached the level where it could be done in places outside of federally funded research centers where you have 300 PhDs in one building, like say JPL. And I studied using GPS a big earthquake in Mexico, the 1995 Jalisco earthquake, and I knew what went into building a GPS network. I knew what went into the data analysis. I knew what went into the models, and it always struck me as a graduate student that there was no continuously operating geodetic network in the only subduction zone in the lower 48 that mattered, which was Cascadia. And towards the end of my graduate career, I started to learn about a group at Central Washington University that had started to build some stations out. And so I, defended my thesis in 1999, and it was obvious that if there was going to be a GPS network in the Pacific Northwest in the Cascadia subduction zone, it was going to be run out of Central Washington University, and it was a nice place to live to boot. And so it was just kind of a very easy jump for me. And it turns out that was the, staying close to the data, staying close to the science, actually turns out to be, it turned out to work out very well. I've been there 23 years, and it's just been one new thing after another. And so that's why I went there, was because at the time, the Cascadia subduction zone had 5 operating stations in 1999, and now we have about 200. And the network that CWU operates has 270 from Cape Mendocino, which is the southern end of the subduction zone, up to the Canadian border. And then we exchange data with the Canadians. And so it was just, the decision to go from Caltech to Central Washington University was totally a function of sort of how Caltech molded me, I should say. So I feel like that's been, that was the right decision for me on many levels. And although it did raise some eyebrows at the time, I will say, because CWU does not have a PhD program. And more than one faculty said, well, are you going to be able to get any research done in between your teaching loads? And I said, I don't know, we'll see. And the answer is, it's not a research university. It's not that kind of place. On the other hand, that guiding principle and training and sort of intellectual outlook on life that I think Caltech really gave me has, perhaps to the consternation of my colleagues up there, constantly redirected me back towards research.
Tim, when you talk about the maturation of GPS in seismology at the turn of the century, is that more a technological or an administrative maturation?
Very much technological. It just, as software developed and algorithms improved and bugs got fixed, and computers got faster. You could now do stuff, on a desktop computer that required, 10 years before a lot more infrastructure.
Tim, as the only one in the lower 48, I wonder if you could speak to what's so unique about the Cascadia subduction zone.
Well, from a seismology or geology or geophysics standpoint, there's really nothing unique about it other than it's ours, right? And it's under Washington, Oregon, and northernmost California and British Columbia. In terms of rates of convergence, it's actually fairly slow. It's quite a low convergence rate. So that means you don't tend to see as much as you do when you go to very, very active places like Japan or Costa Rica, for instance, where you can barely visit the country. If you stay there for any period of time, you're going to feel an earthquake. And that's not the case in Cascadia. It's a beautiful part of the world. That was important to me as well. And then in time, what the Geodesy showed was the subduction zone is extremely active. The big fault. You just got to know how to look at it to see that activity. But we have these things called slow slip events, and for the first 6 or 7 years, they were only detectable through the crustal deformation measurements that GPS provided. In time, seismologists in Japan, using a very, very quiet network of borehole instruments, were able to tease out a seismic signature. And then once they kind of showed the world, here's what the seismology looks like when these slow slip events are happening, then everybody else could tune filters and whatnot and build arrays. And now we see those routinely. And it's a very esoteric seismic signal. It's kind of like a noise. It's a high frequency signal. But that came out of a lot of the initial work came out of the GPS crustal deformations in Cascadia. And that's a gift that keeps on giving because, well, one of the things we figured out was that they're very, unlike most earthquakes, these in one part of Washington state and southern BC, these things have a drum beat regularity every 14 months. You can design network deployments around them, which is really remarkable. And we published that paper in 2001. And that drumbeat periodicity is still going on today, 22 years later. So, but that's a very special part of the subduction zone. So that's one aspect that's quite interesting. Another interesting aspect is that the earthquake culture in Cascadia, meaning Seattle, Portland, Everett, Olympia, Eugene, that's not nearly as developed as it is in California. And so when you combine a lack of earthquake culture, and that's manifested in, really crummy building codes and a historical legacy of a lot of really dangerous buildings, unreinforced masonry and whatnot, and then you combine that with a very big subduction zone fault, you do have the makings for a really substantial catastrophe. The odds that we see it in our lifetime are pretty small. It's been 320 some odd years since the last one, and we know the recurrence interval. But, it's these slow, when I'm teaching this stuff in my classes, though the analogy I use is if you've got your head in a guillotine and the blade is up there and that blade creaks a little bit, that's interesting, right? So, in a way, and that's a little bit what these slow slip events are like.
Tim, I wonder if you can talk a little bit about the concept of extrapolatability. In other words, your close proximity to Cascadia subduction zone and the fact that besides it being ours, so to speak, it's not terribly unique. With all of that in mind, what have you learned about it that says things more broadly on a planetary scale about subduction zones?
Well, even as mellow or unexcitable subduction zone as Cascadia, if you know how to measure it precisely enough, it's extremely active. It's very alive. And we can see these events happening again and again and again. And so that stands to reason that, all these other convergent margins that don't have the instrumentation density that Cascadia has are probably also extremely active. Certain places, like most notably Japan, which has the world's best networks, we know that they've demonstrated, incredible levels of activity, far below what most conventional instrumentation can see. But that's a place where at least the northern half of Japan, the convergence is about 9 centimeters a year, whereas Cascadia is less than half that. But we still see all kinds of activity. So it kind of speaks to, if you can put a lot of instrumentation in there, you can really learn a lot about the details of how these things evolve with time.
Tim, what you found about periodicity, Does that get us closer to understanding earthquakes as cyclic events?
I wish that were the case, but I would have to say the preponderance of evidence is no. If we could watch this periodicity for a couple hundred years, and then watch how there's many theoretical models and fault dynamic models that suggest this periodicity should change over the course of the earthquake cycle as a big fault matures and gets ready to break in a big earthquake. And then there's also reasons to think that the locus of where this slow slip happens should start to propagate up dip towards what we call the seismogenic zone. If we could observe for a couple centuries and see that pattern, then the question would be absolutely, but it would be incredibly instructive. But, we've only been doing this for 25 years, and that's a very small delta T when you're talking about a 600-year recurrence interval.
I imagine then if it's not useful yet for understanding earthquakes as cyclic events, that won't tell us very much that could get us closer to earthquake early warning, or dare I say even earthquake prediction.
Yeah. So the reason I'm hedging here, you gotta be, how do I say this nicely? Earthquake prediction is a magnet for really bad science, and there's 100 years of really bad science based on the holy grail of predicting earthquakes. And let's see, what do I want to say? When you start to get into the idea that certain things are periodic, that leads very nicely into the idea, well, if it's periodic and it's been some amount of time since it happened, you can P-word predict when the next one is going to happen. And yes, we do that with these slow slip events. But one of the things we've really come to understand with Cascadia and other subduction zones around the world is there are certain questions in science that are essentially unanswerable and almost not the ledger domain of science to attempt them. So for instance, like, what's the weather going to be at 2 p.m. in Pasadena on Saturday of June 19th of the year 2351, right? I mean, there's so many nonlinear dynamics in there that's not really a scientific question. And if you go to the earthquake fault world, what we find and what this instrumentation has in Cascadia and elsewhere has discovered is that, you can have, there's not just the big earthquake and then 500 years of nothing. What we see is a very nonlinear, very complicated world where you have slow slip events that can trigger other slow slip events, that can trigger earthquakes, real earthquakes, people shake, feel them. And then that slip then triggers other slow slip events that then propagate down dip or up dip or sideways, which trigger other earthquakes. And so there's this feedback going on between slow and fast slip on a continuous basis. And so then to say, well, just because you're seeing maybe 200 kilometer north-south distance of a 1,300 kilometer subduction zone, a periodicity of every 14 months between, say, 1980, push it to about 1988 through 2022, what does that mean for the greater subduction zone? Well, we just don't know. And I think what we're coming to the conclusion is the predictability of if in the absence of any, paradigm-shattering discovery, the predictability of earthquakes is non-existent. And the combined seismic and geodetic instrumentation that we studied in Cascadia shows that to be absolutely true. And there's a couple of beautiful examples in Ecuador. It came out of a French group where it's a very active subduction zone, and they had big earthquakes. They had a small earthquake, which triggered a slow slip event, which triggered another slow slip event, which then triggered a big earthquake, which then triggered another slow slip event that propagated back up to the original one and kicked off a big aftershock, and then all over the space of a couple of years. So, so to be able to turn that into some measurement of predictability is nuts.
Tim, as you've already alluded to the idea of a non-scientific question with all of the nonlinear dynamics at play, it's a question probably as much philosophical as it is scientific. So if the prevailing idea nowadays is that earthquakes are unpredictable, that seems to me it still leaves us with two options. One, that's a statement of our limitations, both in observation and theory, or it suggests that, earthquakes are fundamentally chaotic, that there's no scenario in the future where no matter our technology, no matter our theory, no matter our observational skills, there's nothing fundamental to earthquakes that could tell us when they might occur. I wonder what your thoughts are.
Yeah, I think it's the latter, entirely. I mean, again, barring some earth-shattering discovery, there's nothing that I've seen that survives, really good scrutiny, any kind of precursory anything that you could actually point to. And again, going back to the weather analogy, to be able to exactly pin down what the temperature in Pasadena at 11 a.m. in the year 2032 is going to be might be impossible, but you can put some statistical bounds on it, and to the extent that you can make these measurements and understand what roughly the climate is in Pasadena at any given time, then that is, I suppose, useful. I mean, if you're coming in from another planet and setting up shop, you would want to know those informations, right? I had another thought. What was it? I get this question sometimes from press up in Washington or about, well, if predictability is impossible, what good is it? What good are you? Essentially, which. These people are not trained as scientists, so it's a perfectly reasonable question for them to ask if they aren't aware of the issues. And another analogy I give is, I was like, your incipient car accident isn't predictable either. But you go through your life making some plans, right? You put on a seatbelt, you buy a car with airbags, or you vote for the politician who will mandate that airbags be included. You do this stuff. And I always think when I'm talking to the press and up in the Northwest, I will say things like that. Like, if you know they're coming and you can characterize how big they were and you can characterize tsunami inundation, then you can make some decisions today, kind of the equivalent societal decisions of making people put on seatbelts. Like, don't build your house in a tsunami zone, or build buildings. Don't allow unreinforced masonry to be built anymore in Seattle. Things like that. So it has some value to it.
Tim, just a parameters question. What are the thresholds by which you determine a slow earthquake? How slow is slow, and when do you get to fast?
Yeah, exactly. Well, that's a good question, because it turns out the more broadband the measurements you have to actually study these things, the more you realize these are the rate of slip and the duration of these events actually fills most of the spectrum. And we know from an instrumentation standpoint that we have big gaps in our detectability window. But I would say in Cascadia, these things turn on and we get a couple centimeters of fault slip, typically between 25 and 40 kilometers depth, which is a lot deeper than the seismicity of Southern California. And during that time, we get a couple centimeters of slip. So a couple centimeters over 4 to 5 days, say. Compare that to, a conventional earthquake like, let's say, what's the recent one? Northridge, for you guys, that had maybe 10 to 15 centimeters of slip over a roughly 10 kilometer patch. That happened in 6 seconds. And so if you think of energy, the source of a fault is just energy, seismic energy released into the solid earth. When you're taking and spreading it out over days, this is why it wasn't visible on typical seismic monitoring for a long time. But it still deforms the earth, which is why the geodesy could pick it up.
We talked about the maturation of GPS at the turn of the century. Where is it now? What are some of the key technological advances 20-something years later?
Well, so this is really a close to home question, because it's, again, this network that we run out of CWU. When I got to CWU in '99, we had 5 or 6 stations, and we had modems attached to these stations, and the data, the GPS receivers would stream to a data logger, and we had modems, and none of my students know what a modem is anymore, and because the phone rates were cheaper at 2 in the morning, some cron would kick in and dial up 6 stations over a 56K modem, and that was actually towards the end of the modem world, and download this data. But in time, starting around maybe 2002 or 2003, receiver manufacturers started to put an Ethernet chip on board. It was just cheaper to plug it into Ethernet. Okay. And that got rid of the modems. And this is really interesting because then we had to, deal with, now we have to catch the data continuously at CWU as it's being acquired, because the speed of light's fast, right? So whether you pick it up in Seattle or the coast of Washington or the coast of Oregon or out on the coast of British Columbia, it shows up at CWU in a tenth of a second. And so we had to think about what we were doing and how we weren't going to be using modems to download batches of data. But it took exactly no thinking whatsoever to realize that if we're getting data from all over Cascadia is effectively instantly, then we've got the makings of a seismic network that isn't built out of conventional seismometers where you've got a magnet inside a coil with some feedback circuitry. Instead, you've got a GPS antenna listening to satellites, but we're getting that data in real time. We know how earthquakes work. If we actually get a big one, some of these stations are going to move 5 meters, right? And we'll know that instantaneously. And so in 2006, this was the first proposal, I wrote a proposal to NASA saying, hey, look, this is totally bleeding edge pie in the sky stuff, but we've got 50 stations out along the Cascadia subduction zone. We can build a seismic network out of this, a very coarse seismic network. And you got to be really careful here, because a really good, like the Pasadena Struckeisen, if it's still a Struckeisen there, it's got a sensitivity. It's a million times finer than what GPS can do. But when your station's moving a meter in a minute or 5 meters in a minute, you actually don't need you don't want a Struckeisen for that. You want a blunt tool. And so we pitched to NASA, like, we think we can build a very blunt GPS-based seismic tool that will tell you, basically if you have good coverage over the timescale of the rupture itself, which for a big earthquake might take 30 seconds to a minute, that's the time where the fault's actually sliding. We can capture that information instantly and tell you instantly how big your earthquake was. And NASA bit. And so that started what I've been kind of working on for the better part of 12 years is building a strong ground motion, meaning blunt, GPS-based seismic characterization tool. And we started in Cascadia, but the rest of the world caught up. And so now what we're doing is we've expanded it globally. And so we're pulling in a couple thousand stations from around the world, and we get it anywhere from, Antarctica comes in half a second. And we position it in a very well-defined reference frame, and we take those positions and we send them on to, there are in this world, there are certain agencies that are responsible and required to be responsible for certain things. Our USGS owns earthquakes, NOAA owns tsunamis, and NASA isn't supposed to do either, but sometimes they do. And so we send these positions from the GPS receivers from essentially all over the world to the National Earthquake Information Center in Golden, Colorado. We send for the West Coast, we send them to Caltech, to Berkeley, and to University of Washington for Shake Alert, the earthquake early warning program. We send subduction zone relevant or just ones they want to the NOAA tsunami warning centers. And they've hooked those in with different algorithms to use these measurements to rapidly characterize the magnitude of a GPS. Because if you actually wait on the global seismic network, if you have a big earthquake, say in Tonga or the Solomon Islands, say, and you wait for the PNS waves to propagate out through the planet, and what is used is something called a a W phase inversion, which came out of Caltech, Kanamori and Anderson, I believe, in maybe 92-ish. That's the standard way of characterizing a big earthquake quickly, but you got to wait for the PNS waves to propagate around the world. So you're looking at 15 to 20 minutes, which is greater than the inundation time at the local coastline. So if you've got GPS out there in sufficient coverage to characterize the earthquake, you can turn it around much, much quicker. And what we're finding is that in practice for like the tsunami warning, they're very conservative, and as they have to be. And so if they have what smells like a big earthquake, they hit the red button. But what the GPS is allowing them to do is, again, they're going to hit the red button no matter whether GPS or not, but it allows them to, and we've had a couple examples of this, like up in Alaska, where there was no geodetic offset. And so that change, that meant the focal mechanism of the earthquake was different, and allows them to cancel the alert real quick, which actually is good for them because it doesn't, people get inured to alerts. If there's constantly alerts coming and there's no tsunamis, people start to ignore them. So it helps them avoid that problem. It helps build confidence in the system. It helps them have confidence in their solutions. And so that's kind of, but again, it came out of this evolution of the technology, and then our network, what's called PANGA, the Pacific Northwest Geodetic Array, kind of marching on the heels of the technology, and just kind of surfing that wave, so to speak.
Tim, are you a founding member of PANGA, or does it predate your tenure?
It actually predates my tenure. The two people who hired me I think they were a husband and wife team, and the wife, Megan Miller, I think actually wrote the first proposal to put the first station in the ground. And she was picked off. She was a postdoc at JPL, and I think she moved up there about 4 years before I did. And then her husband, I think, was the one who actually came up with Panga. That's a pun because they liked Mexico, and Panga's a Mexican fishing boat. So no, I wasn't. But I got there in '99, and then by 2001, Megan had decided to go into administration, so she became a dean. And so the lab was actually unceremoniously dumped on me. And I had other things to do. I had Don Helmerger yelling at me to get my thesis published because his funding was running into trouble. And so I actually had no interest in it, but it was somebody had to do it, and I'm glad I stepped up.
A few overall questions to your research. So among the fields and disciplines, there's seismology, geophysics, geology, earth science. At the end of the day, what would you call yourself? What's your home discipline? Geophysics.
It's funny. I went to graduate school to do seismology, pure seismology, and this is also a very okay. I'm not. Is Hira going to listen to this?
I hope so.
All right, Hira, this one's for you. So I went to study seismology, and that's what I intended to do. However, between undergrad and grad school, I worked for the USGS for 2 years at the Cascade Volcano Observatory, and they were putting GPS on volcanoes. And so that's actually where I first learned how to build a station on some very fun volcanoes like St. Helens, Rainier, one called Augustine up in the Cook Inlet of Alaska. And at Caltech, you have these thing called the orals exams. In theory, they want to make sure you know what science is and then kick you out if you don't do well enough, right? And so you have to have these two independent projects. And one of them was to work with Joanne Stock, who was building a geodetic network in Jalisco, Mexico, which is also a subduction zone. And she was interested in the continental dynamics aspect because it's a big uplifted terrain that hasn't quite busted off mainland Mexico and become attached to the Pacific plate the way the Baja Peninsula has. If you look on a map, Baja is here and then Jalisco's right here. And Jalisco's undergoing that process right now. And in 10 million years, it's going to be following Baja up into the Aleutian Trench. But anyway, so one of my roles project was working with Joanne on this stuff, and but the continental deformation rates in Jalisco are very low, and I was like, I don't want to be a grad student for the 12 years it's going to take to get a resolvable signal here. So once I kind of got through my orals, I was very I went and talked to Joanne, and she was incredibly gracious. And she's like, "Yeah, it's going to be a while, and you came here to do seismology. Go thrive." And that's one of the really, really special things about the Seismo Lab. And I hope it's still like that. That students can just kind of follow their interests, and also the vicissitudes of fate that throw projects at them and whatnot. So anyway, I forget the deal. I think I was just auditing a class that Hiro was teaching. And the Hiro came in to this class. Would have been about a year later. And he said, "Tim, there's been a very large earthquake under your GPS network." And my headspace was in trying to understand Canyard de Hoop, which is a totally esoteric way of solving a wave equation. And I looked at him and I said, I don't remember what I said. I said, "Huh." And Hiro looked at me and he says, "Huh?" And I'm like, and I just, I couldn't process it. I was like, what does this mean? And at the time, it turned out it was a really big earthquake. Now, knowing what I know now, I mean, I'm like, God, that's like 10 theses right there. I mean, talk about fate handing me a golden egg. And so I was watching, industrial strength Caltech seismology ongoing about this subduction zone earthquake under Jalisco, Mexico, where Joanne and I and her crew had built this network and gotten a measurement. That's the key thing. They installed it and built it and got the initial measurement. So we knew where stuff was, at the centimeter level before the earthquake. And I remember Hiro just looked at me, and what he was seeing was, some kid who's dumber than a box of rocks who can't seem to process that there's been a massive earthquake under their geodetic network. Of course, Hiro knew everything that was going to come out of it, but I didn't. So anyways, it took me a day or whatever, but I very sheepishly walked back into Joanne's office the next day, and I said, "Hey, if you don't have any students to work on this, I'm not that stupid. I'll work on it." And she was very gracious. And it turned out it was just, we saw all kinds of stuff. And it was 1995. I mean, the subduction zone had broken. It wasn't done breaking in the weeks following. It kicked off all these slow slip events. Those slip events were clearly triggering aftershocks. But now we could see this stuff because we had flown down there and put all this GPS out. And it took us 4 or 5 days to get down there after the earthquake. And then in time, half my thesis, I ended up working on that for a couple of years and published a bunch of papers. And then there were other faculty with other grad students. So eventually I kind of had to move on to other stuff and share the wealth, so to speak. But so in any case, that ended up leading down to understanding how to put in GPS and analyze it and monitor it and all of that. So I think that was your question, right?
Yeah, exactly. Tim, what aspects of your research agenda are more on the theoretical side and what are more on the observational experimental side?
Can we take a 30-second break here, David?
Yeah.
I'm going to move locations because there's a bunch of background noise that just happened here, okay? Hold on, give me a moment. Sorry about that. Because I'm traveling, I don't really have a private place to talk with you.
No worries.
Okay, can you repeat the question again?
Yeah, so the question was just your overall research agenda. What's more on the theoretical side and what's more on the observational experimental side?
So the vast majority of my time over the last 10 years has been spent with my group trying to increase the precision and the reliability with which we can position stuff to, centimeter accuracy. In conventional GPS, you you download 24 hours of data. So you have a ton of measurements, and then you extract from that, you estimate a single position based on 24 hours of continuous measurements. What we're trying to do, where you make a position estimate every second, like a 1 sample per second seismic instrument, you have 1 second of data, and so you end up having quite a bit bigger scatter, and then you have other vicissitudes of this kind of thing. So it's very demanding. And so most of the stuff that I've been working on is really trying to improve the reliability and the resolution. Like if we could actually measure stuff routinely to what we like to use legumes, like if we could measure things precisely to the phase center of an antenna to the volume of a lentil, we could really see very fine earthquakes. We're somewhere between an orange and a grapefruit now, continuously 24 hours a day. So that's kind of been just positioning, and it's very similar to seismology. You get you have GPS at its heart as a ranging measurement, and so meaning if you know where your satellites are and you can get a range to the satellite, then you have a sphere on which you can exist. And if you do it with a bunch of satellites, you have intersecting spheres, and there's one point where you can be. And in conventional earthquake location, the ranging measurement is a S minus P time run through a travel time curve, and you get a range to a seismometer. And then you do that with a bunch of seismometers, and you get these intersecting circles, and you get a position. And so it's a very similar thing, but it's atmospheric dynamics. There's ionospheric dynamics, there's orbit issues and satellite clock issues. And so I would say it's equally that. And then it's also actually just working with network operators to get data sets freed up around the world. That's been sort of something I've been working on the last couple of years. The pandemic really, really messed that up. So we're about where we were in mid 2019. Because these networks are very expensive to build, they're expensive to operate, and people often don't want to share their data, or they can't by national law. So if you're trying to get, Chile to open up its data sets, well, there's issues there. Or if you want Japan or New Zealand or whatever. So I've been dealing a lot with that. Training graduate students. We have a master's program, so they only resident for a couple of years, and then they go on. Typically, the best ones go on to do PhD students, where everything we taught them, they then finally use. And then teaching, and that's kind of the job.
Well, Tim, let's now go back, establish some personal history. As an undergraduate, was seismology already on your radar? Was that something that you were already interested in?
Yes, definitely. Earthquakes I grew up in Southern California, and earthquakes were things I had felt, and I thought, well, that's pretty cool. And I went off to college as a physics major, and that was that was something I was very interested in. And then in college, I discovered the whole outdoorsy world, and I was exposed to a former Caltech faculty member, a guy named Brad Hager. And I realized he was doing mathy, physicsy stuff out in the world, and he got paid to go out and go camping and put out instruments. And I thought, that is for me. That is what I want to do. And it was some combination of kind of being math and physics oriented and discovering backpacking and outdoorsy stuff.
Where did you do your undergrad?
Well, I started at Reed College in Portland, and Brad was the one who told me about a program where you could be a physics major up there and then transfer to Caltech. So I actually did that program, and it was dynamite. I mean, Reed was really, really good at all those humanities stuff, and I still think the most important skill I have is the ability to write a proposal. And all that humanity, all that, I don't know how many literature classes we had. I mean, just writing papers and papers and papers and more papers. And as a physics major, getting the basis. But then when I did that transfer, and I don't think that program exists anymore. I think it went away a long time ago. But I think getting thrown right into just full Caltech undergrad thing. I mean, electrodynamics taught by Jackson and Feynman's math book, and I mean, it was pretty hard. And so I kind of was. That's why I took a couple of years off after college, because I don't want any more of that. But after a couple of years of working, I was like, well, actually, I think I do want more of that.
And the program was 2 years at Reed and then 2 years at Caltech?
3 at Reed and 2 at Caltech.
Oh, so the 5 years, is there a built-in master's in there?
No, you just get a bachelor's, but you get a good bachelor's. So, yeah, and I really came to value that. I remember when I first showed up, years later as a grad student, there was a professor in atmospheric sciences, Andrew Ingersoll, and he was in charge of giving out this test of math and sciencey skills to incoming students. And I took this test and I just crushed it. I remember thinking like, either this place is easier than I expected, or I really got my money's worth out of my college experience. And I just remember and that was where I think a lot of the Reed stuff really helped. I mean, the chemistry classes there were hard. I'm not a chemist, but I really did learn that stuff inside and out. So, when they're like, what's pH? I know what pH is. What's electronegativity? How does this reaction work? What's the equilibrium constants? And I'm not a chemist, but even today, I still remember that stuff,
Did you get to hang out at the Seismo lab as an undergrad?
Not really. There's no mixing. I'd see these people in the coffee room, and I didn't really know much about it.
And you knew you specifically wanted to take a break, not to go straight to graduate school.
Yeah, absolutely.
So what were your options? What were you considering when you graduated?
Well, I did like everybody else. I applied for a bunch of jobs, and the final choices came down to it was actually a stark choice. It was really fun. It was very telling. One was a geophysics entry-level position at Unocal at their thermal plant in the Salton Trough in Eastern California, Salton Sea. They geothermal energy plant there. And, it's Unocal, it's oil. So, and the salary was just over the top. Like, I had no idea you could be paid that much as a 23-year-old. And so that was actually very compelling. But then the other job was, I remember it being, okay, so this would be, you got to put this into 1991 dollars, but I recall Unocal offering about $70,000 a year. And the other job was this USGS job as a GS5 up in Vancouver, Washington, at the Cascade Volcano Observatory, which was at like $23,000 a year. And it was decision time, man. And but I noticed the Unocal people were very formal, and the USGS people were very casual. And I noticed that the Unocal people were in the Inland Empire, way down in San Bernardino, and the USGS people were in Vancouver, Washington, and got to fly around in helicopters into volcanoes. And, and you're 23 and you're not really thinking about like retirement or any of that kind of stuff. And so I took the USGS job, and I don't know, maybe I'd, be richer than Midas if I'd gone to Unocal, but who cares?
Tim, did you have an appreciation of the historic connections between Caltech and the survey? Did that influence your decision at all? No. I was just looking for a job. I knew I needed a job. I didn't have any money. I didn't have any income. I needed a job. And, so I was looking all over just needing a job trumped all of that. In time, it would come to appreciate the extent to which, Caltech, the Seismo Lab has an extraordinary legacy. Like when you zoom way out and look at earthquake science, I mean, it's singular.
I would say it's a singular, the place has had a singular contribution to the discipline. But that's Caltech, right? I mean, it's like that. I know it's like that with physics. I know it's like that in AI, Carver Mead and Hopfield and all these others, I mean, they were doing the basic stuff on which all of our Google searches are based, but they were doing it 35, 40 years ago, yeah. Right? So, you just kind of, that's one of the trippy things about Caltech. You get used to, like, there's a Nobel laureate down the hall and just go on about your day and try not to let it mess you up.
Tell me about the work in Washington. What were you doing for the survey?
Well, it was crustal deformation. It was monitoring volcanoes. The Cascade Volcano Observatory was founded very quickly in response to the unrest at St. Helens in 1979, actually, late 1979. No, March of 1980 is when it turned on. It was 2 months between when St. Helens turned on and when May 18th, 1980 happened, as I recall. I don't think it was much more than 2. So anyways, this was a ragtag team that was assembled really quickly by the USGS to monitor that volcano. And then after the big eruption, the volcano continued to erupt sporadically through about 1986. And then it as they do, it kind of mellowed out for a while. And by the time I got there in 1991, it wasn't really doing much. But what we were doing was we were measuring the deformation of the volcano. And even though it wasn't erupting, it was still very active. And so the measurements then were 2 types. One was a leveling. So you go up and down a road with leveling rods, which sounds archaic, but even today in 2022, if you want only vertical deformation profile, the most precise way of doing it is still a leveling line. Good old fashioned 100-year-old technology. And the reason GPS can't do it better is because of the incredible correlation between travel time through a variable velocity atmosphere and clock and satellite are those just destroy your vertical repeatability. But so that was one measurement, was leveling lines, and as a GS5, my job was to hold the rod and then let the big pro GS7s actually look at the look at the gun. And then the other one was just a laser pinging, 2-way laser travel time. And so but you got to get in a helicopter and fly up into the caldera and hammer one of these mirror reflectors onto some, steaming hot wall of rhyolite, and then get out of there. And I remember I enjoyed that immensely. Nobody was allowed into the caldera of St. Helens unless you were USGS. And one of these cracks, I looked inside it and it was glowing red hot in there, just a meter below the surface. And so we're like drilling a hole and putting this thing in there and hoping nothing happens. And you didn't spend a lot of time inside the caldera in 1991. The chopper would drop you off, you do your thing, and you get out of there real quick. And so, what is a 23-year-old, I mean, I don't know, again, maybe I'm atypical, but that was a very exciting job. But I will tell you, I was at it for about just over a year and maybe 15 months. I realized this avalanche of learning that I had been dealing with that had burned me out pretty totally over the last 5 years had stopped. And this is what caused me to want to go to grad school. I was like, I'm not really getting this. I just felt, and I don't want this to sound like in any way an indictment of the USGS. I mean, there were really smart people there, but I was like, I'm not done with this process, so I'm going to sign up for more punishment. I just kind of realized that I wanted to keep getting more knowledgeable, and the rate at which, and maybe this is just reflective of me, but 1992, the web hadn't been invented. You couldn't just get interested in something and go find out about it. But I realized that I wasn't done yet, and I wanted to go back to school. And so I only applied to a few places. Joanne Stock was like, you got to go back east. I'm like, I'm not going back east. And so I applied to Caltech. I applied to Scripps. And I think I applied to the University of Washington. And I didn't think Caltech would take me, honestly, because it seemed like a bad idea. I don't know. But then they did. And I was like, well, I'm going to do seismology, given that, names like Benioff and Gutenberg and Richter, Helmberger, Kanamori, Anderson, on and on and on. I'm like, I would be an idiot not to go there. So that's how I ended up going back. Did you have a good idea, since you were knowledgeable of the department already, who your thesis advisor would be? No. Caltech's really special that way. They kind of, I don't know how the faculty sorted out, but they just kind of sorted out. No, I wasn't beholden to anybody. And that was why Joanne was so incredibly gracious to let me work on her Jalisco project as an orals project. And then when I was like, hey, I'm going to go do this other thing, and then she had a big earthquake to let me back and work on it. I mean, I've not heard of that happening any other place except Scripps. I think Scripps does it that way too. And I don't think it's a function of money. I think it's a function of faculty values, and which really makes it an amazing thing. And again, I hope it's still like that. I've been gone for over 2 decades. So tell me about the Jalisco project and what was compelling to you about it. Well, it's fun because so as a first-year graduate student or second-year graduate, you're learning a lot of things simultaneously. You're learning classes. You're learning, in my case, I was a C programmer of sorts, but not in a Unix environment. So there's this whole dealing with Unix and learning how not to cat binaries to a screen and yada, yada, yada. And so you're going through this massive learning curve as a first-year graduate student. And then eventually kind of get the hang of it, and things start to make sense. And you're parsing numbers, and you're writing little scripts to do little things. And you pull out all these numbers, and you're learning this. It was fairly new at that time, plotting routines called like generic mapping tools, learning how to make plots. And at some point in all this just numbers and stuff and computers, I finally make a vector map of how things move before and after the earthquake on all of our stations. And I remember the first time it popped up on the screen, it was so beautiful. It was like Mother Nature just tugged on the crust of Jalisco, and all 13 stations just went just like it was made of rubber, the way this just popped out of all of, weeks and weeks and weeks of crunching on numbers. That for me was probably the coolest. I think that's the singularly coolest moment in my graduate story, was just seeing this stuff. And I remember parading it all around the 3rd floor of the Seismo lab. Look at it, it worked. It's a click, 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 click. And then of course that was between, a year before, or 10 months before the earthquake and 6 days after. And then when you looked at between day 6 and day 7 and day 7 and day 8 and day 8 and day 9 and day 9 and day 10, and we went out to about 18 days or something like that. That crust just kept moving, many centimeters, well within our resolution, and that meant the fault was still sliding. So what does that mean when you have an earthquake, but the earthquake doesn't turn off? It festers for days and days. That was the beginning of the earthquakes aren't just this thing that happened. They're part of a very dynamic landscape or spectrum of behavior. So that was cool and very interesting. And then so we could map out not just where you get these offsets, and then if you think you know where the fault is, it's just a matrix inversion to figure out what distribution of slip both best predicts those offsets that you measure. And then you can do that again over time. You can see these slip patches propagate around, and as they propagate sideways, they're kicking off aftershocks that pick up on the seismic network. And so that was far and away the coolest aspect of the project. Driving around back roads of Jalisco was also very cool. Jalisco is it's a part of Mexico that's very much unlike any other part of Mexico. It's where a lot of the Mexico had a thriving film industry. So if you ever saw old 1940s Mexico films, chances are they were filmed in Jalisco. Jalisco owns the trade name to tequila, so that was cool too. There's a lot of distilleries out there. I think with the narco traffic problems these days, we probably couldn't get into a lot of those places now, or wouldn't dare, but it was cool then. But that took a distant second to the science itself. Yeah.
Tim, more broadly, between coffee hour or just interacting with fellow students or faculty, what were the big ideas? What was animating people at the Seismo Lab when you were a grad student?
Well, I think okay, so certainly coffee, because Hiru was far and away the most religious attender of coffee. I mean, he started it because it was his coffee break. Oftentimes it was what was he interested in. And during my time, he was very interested in fluids, fault fluids. It's moderating or triggering earthquakes. If fault fluids exist in a fault at the overburden pressure of the rock, then they're prying the fault open, which should enable it to slip. And so there's lots of reasons to this day. But Hiru was very interested in that. Helmberger, who ultimately became my thesis advisor, had discovered, and his other students had discovered these ultra low velocity zones on the core mantle boundary, which were very, very detailed, but incredibly low, like 20% below a reference velocity things. And so ULVZs were a big deal. Fault fluids was a big deal. Trying to think about Joanne had a lot of students. She was going on a lot of research cruises off of Antarctica at that point, mapping out the plate tectonic history of Antarctica vis-a-vis, I don't know what other plates, Southern Indian Ocean or something. And she needed those because she was working on these big global plate reconstructions, and a lot of uncertainties in the whole global reconstructions pinned down to what was going on off of there. So there were always students coming and going and telling stories about getting trapped in the Drake Passage between the Antarctic Peninsula and southern South America in 110 knot winds and whatever. What else? Rob Clayton was running all kinds of seismic lines, LARS, I think it was called, LA Reflection Seismology Experiment. There was LARS. I might have just mangled that acronym. I just pulled that out of my head after 23 years, but there were all kinds of seismic reflection lines being run all over LA. So I got to help out with one, which was kind of fun. It was the Hood, my station, at 2 a.m, like Hoover and Manchester, south of the Inglewood Forum at 2 a.m. That was okay. I would say those were the big themes. There was I have a mild criticism. It's only mild. The Seismo Lab faculty had not kept up with computer times. And so there was a couple of years there where we didn't have the computer power that we needed. They were trying to keep an old mainframe going, a Solborn, as I think it was called. And meanwhile, Linux had come around, and the students just blew right past the faculty on this. And we were all going out and buying PCs, like PC, like personal computer. We'd go to these flea markets and get motherboards and chip controllers and hard drives and put them all together and put Linux on it. And these were far faster than what the Seismo Lab had available to compute with. And that ended up, computers are a rat hole that you can go down that get in the way of doing science for sure. And so I don't remember when that would have been, about 1996, 95, 96. So I was like, today what I know is like computers are the least expensive piece of this equation. Throw money at that problem. And of course now everybody's got their own, MacBook Pro that's a supercomputer, so it's moot. But that was a big thing. We were kind of building our own computers because the system in the Seismo Lab sucked. Let's see, but I don't mean that. I don't know. That's a mild criticism, and I don't know what's going to be shown, what people are going to get pissed off at or not. No. Understand that's a mild criticism.
Tim, you mentioned computers. This is going to sound like a long time ago, but what about the internet? Was the internet fully embraced for seismology at that point?
Yeah, definitely. Yeah. So a lot of the seismic data, we just downloaded it from the DMC, the Data Management Center, which was run by the NSF through a contract to IRIS. So yeah, that had come in, but the web came in right in the middle of my graduate time, the World Wide Web, which is just an overlay, right? But the idea you could have a Mosaic was the first graphical browser, and that changed everything really quick. And I think a lot of the Seismo Lab PhD graduates who didn't end up sticking with pure science went off to Google's or the big software houses. I know a few from my year. I guess one other thing I would point out is there was this is something I've struggled with a lot. I've asked myself many times, was Caltech good for me? And I mean, the overwhelming empirical evidence is, yeah, it was incredibly good for you. But there was so much stress as a graduate student of you just aren't good enough. You're not smart enough. You're not working hard enough. You're not, and in time, what I came to understand was that the dimensionality of human cognition is vast, and you're going to know something that somebody else around you doesn't know, and that everybody except the faculty felt inadequate there. And I've compared notes with other students. They're like, oh yeah, we all felt that way. I'm like, well, maybe that's just the baptism by fire that you have to go through. But we all kind of hit it the best we could. But I've often thought, I wonder what that did to my psyche. And I don't mean that in any disparaging way whatsoever. I have such extraordinary thanks to the entire lab, all the people who were there. Also, you learn as much from your fellow students as you do from advisors. But I won't say it came at no cost. It's a very stressful. It was, and I suspect it still is. It's a bunch of motivated people who are focused and working hard. But it was very stressful.
How much of that was inward directed, just you competing against yourself, and how much of it was you looking around at the other graduate students?
90-10. Grad students were helpful, and I certainly always tried to. There were always a few exceptions, but I always tried to help if I could. There were always people who knew more about computers for sure. But mostly it was just this inadequacy of like, I'm never going to be as smart as these faculty here, And, I had a lovely out though. For me, when the stress got too bad, I just go for a run. I'm a runner, a slow and middling but dedicated one. And I was like, okay, you got the Arroyo right there. Get in your car, go run 10 miles in the Arroyo and come back, and things won't seem as bad. And that's pretty much was the case. So,
Tim,
it was a very stressful place.
For the research, when did you know you had enough to defend? When did you feel like it was a complete project?
That was really interesting. That's a good question. It hit me. I think I'd been there 5 years at that point, and I was like, I'm done. Like, I know what I'm doing. I need to get out of here. And I went, and at that point I was working entirely with Don Helmberger. We'd published 3 papers. And that's not counting any of the Jalisco earthquake stuff I had done. I was like, Don, I'm gonna get out of here. Like, I've done enough. And he was like, yeah, I agree. I'm like, well, why didn't you say something? Because of course I'm the most fruitful, I'm the most productive now, right? And Joanne and I, with the Jalisco earthquake, all those papers were out already and published, so there was no real discussion there. And it was just kind of hit me like, I don't want to say I don't need these people anymore, because that sounds so mercenary, and that wasn't the sentiment. But it was more, it was more like the eagle, the rook, the 8-month-old eagle in the nest beating its wings. It's like at some point you're going to take that leap. And it just hit me like one week. I was like, I'm in control. I know what I'm doing. I know why I'm doing it. I know how it was done. I wrote every one of these papers. I either wrote or know the people who wrote the codes that I'm using. And, it was just kind of like, okay, I'm feeling like I've got the phrase I used at the time is I feel like I've got critical mass between my ears to go do meaningful stuff. That was the phrase I used at the time. And I didn't feel that way at all until I did. And that was about 5.5 years for me.
What did you see as the main contributions or findings of your thesis, and how have they aged over the years?
Well, nobody's disproven any of them, so I guess they've aged well. Might be a bad sign that nobody bothered because it's not worth it. But clearly the advent of continuous geodetic measurements enabled the realization. I remember my thesis defense seminar talking about this feedback between fast and slow slip, and one triggers the other and the other triggers the other, and this is how you get chaos. Chaos theory was still big at that point. And that what Joanne and I and our colleagues teased out of the Jalisco data set has been shown to be absolutely true. These faults are not, the San Andreas fault, say, it's not just this crack in the gallon, it's not sliding. There's all kinds of activity going on, certainly on the deeper reaches of it. You got to be able to measure it. You got to get in there. But that realization that these things are alive and they're doing stuff continuously, and that the big one is just one piece of the total spectrum of how they're active through the decades, that came out of my thesis for me and the papers we published, and that's now widely accepted. I mean, there are a few faults that seem to be dead and totally locked, but they're the minority.
Who was on your committee besides Helmberger?
Tom Ahrens. I'm confusing it with my orals committee because Joanne was on that, but Brian Wernicke was on that, and they got in an argument, a science argument, which was great for me. I figure if you get two of them arguing with each other over your science, you're golden. And but the committee was Tom Ahrens, it was Helmberger, it was Rob Clayton, it was Joanne Stock, and I think Hero was on it. But at that point, it's funny, I'm confusing, as you ask me that, I'm confusing it with my orals committee, because the orals was scary, because I was the one where they're going to kick you out. I mean, you're not going to defend if your advisor doesn't think you're done.
Sure.
And if your advisor thinks you're done, and you've gotten, I think I ended up having 6 papers published for peer review, that's going to be one hell of a committee that's going to hold you back, And so at that, I hope this doesn't sound wrong, but the PhD defense committee is just a rubber stamp as far as I'm concerned. And that's why I'm struggling to remember who was on it.
Anything memorable from the defense? Any questions or debates that came up?
No, what I was, somebody asked why I hadn't modeled the dynamic feedback between slow and fast slip triggering each other. And I forget who asked it, but I was like, that's another PhD thesis unto itself with a very different set of skills and disciplines and theory. And I remember thinking, should I have done that? That's all I can answer. And it didn't. And, that's a discipline. I mean, there's whole divisions working on that problem.
After you defended, were you looking at faculty and postdoc opportunities at the same time?
I was. I had a postdoc at MIT, and I had a faculty offer at University of Washington, and a faculty offer at Central Washington University. And then I think there was the making of a staff job at JPL. I had a kid on the way at this point. And so the idea of a postdoc, if I could have a permanent job rather than a postdoc, was a huge impact on my decision making. The other thing, the postdoc, I was very interested in this whole using geodesy to monitor earthquakes and subduction zones, and I knew this network was getting built up at CWU, and that was more interesting to me scientifically than what the MIT postdoc offered. And so I was like, all right, I'm going to go do this thing at this non-research university and see how it works.
And as you've already told me, quite well.
It worked out. I mean, somebody once said, you're not going to maximize your scientific productivity here, Tim. And if that's what you're gunning for in life, don't come here. And I got to thinking hard about it. And I think that is true. If you don't have PhD students, it's very hard to get papers across the finish line. And you are limited in what you can take on. And I think if I had done, gone to Berkeley and done that, I would have probably have more things going on and certainly publish more papers and whatnot. But that, I don't think it matters. It kind of depends on what provides you affirmation in your world and what's meaningful in your world. And there are times in my job where I definitely get frustrated that I can't do stuff, especially when I'm pretty good at seeing around corners, it turns out. And there's some things that have come, and it's like, I knew years in advance that was coming. And if I had postdocs and the whole package of a Berkeley or a Caltech, I would have been all over it, but I just intentionally couldn't go there in my, when you've got, two master's students and staff. And so I've had to be judicious and strategic. On the other hand, I live in a beautiful place and I walk to work, and, I live on the east slope of the North Cascades, an hour and a half from Seattle. And, that's got measurable benefits as well. So, there's no perfect solution.
Tim, what about
if I could move if I could move the Seismo lab to CWU, I would.
I think I'd follow you. I'm missing the rain in a very big way.
Yeah. Are you from up there?
No, I'm from the Northeast. So this is a very, very different kind of place in that regard, but I love it. I love it. Tim, what about the funding? In other words, are you at a structural disadvantage not having PhD students when you're applying for grants?
Yeah, that's a tough question to answer. I don't see how I can not be. Mm-hmm. The last 4 years of a PhD's typically 6-year residence, they're the productive ones. And if you can use those figures to write your proposal, it's so much easier. However, I just don't. There were times where I was like, I just can't do this. I can't make this work here. I can't go up against the Caltechs and the Stanfords of the world and have a potential this. But I think there's enough to do, and there's enough creativity in the process that even if you don't have all of that infrastructure, you can still, if you can write, and I've got that box checked, you can still make the case for meaningful scientific things to be done that are not going to come out of other groups. They've got other groups. They have great ideas that you'll never have, but you'll have great ideas they'll never have. Mm-hmm. And if you can write and you can pitch those great ideas, the funding agencies seems like they've gone for it. And I've often wondered, well, the funding agencies largely report to Congress, and Congress is going to get pretty irritated if they only fund UC, Caltech, Stanford, MIT, and Harvard, right? They got to spread the wealth a little bit. So I think there maybe what I lack in the infrastructure, maybe there's a bit of a tailwind from the sense of trying to spread the wealth of American science funding to non-big R1s. That's a hard question to answer, but I there are times where, I keep in touch with Caltech faculty, and I see some of the stuff going on down there, and I think, oh God, I'd love to be able to do some of that stuff, but you just can't. So you kind of got to know, it's a little bit like running a marathon. If you're a 5-minute miler, fine, go out at 5:10s and hope you can hold it for 26. If you're a 10-minute shuffler per mile, 10-minute per mile shuffler, well, know that about yourself and plan accordingly. These are not good answers, I realize that, but I guess I don't know the answer to your question. I feel structurally there's no way you can really compete, and yet somehow for going on 24 years we have. So
maybe the answer is in fact yes.
Yeah, maybe the fact is yes.
Tim, to flip that around, specifically, as a product of Reed, being at a small college where teaching is really emphasized, what's the value in that, given that you have that bandwidth perhaps to interact with undergraduates in a way that might not be possible at a larger research institution?
Say the question again. I'm not sure I understood it. Do you mean my time at Reed, or do you mean my time at CWU?
No, just thinking about the value of the education you got as an undergraduate at a place like Reed, where the emphasis obviously is on undergraduate teaching. What's the value that you might have that people, the grass is greener, not having access to some of these things at larger colleges? What might be the advantage or the benefit that is conferred to you just by having more bandwidth, perhaps, to interact with undergraduates?
Yeah. Well, let me give you an example. There was a humanities class we had to take, and I read the Iliad or whatever, and you write an essay, and turn it in. And then the professor sits down and goes through that essay with you, and you get it back, and it's graded, and then the next week you rewrite it again. And the next week you rewrite it again. And you do this for 13 weeks straight. And eventually, somewhere 7 or 8 weeks into this, you've got this perfected essay, but it's kind of a boring essay about the Iliad. And that's when the professor sits down with you and says, well, you've got this, all right, fine, all those nuts and bolts are there, but it's really quite boring. Why don't you bring in what's really going on today in national politics in this country? And I remember at Reed, there was a lot about old growth timber and spotted owl and stuff, and bring that into this essay. And how are you going to combine an Iliad? And so you do this, and suddenly by the end of this course, you go back and you look at the 13th version of this and the first version of it, and what you've got at the end is something you might submit to the New Yorker. It's really interesting. And that one-on-one, this is what writing is. And something like that could happen at Reed, because that's what the place is all about. And so now you have this kind of gold standard of what true education is and how incredibly expensive it is, because that's kind of a one-on-one type of thing. And I take that, and when I'm dealing with my own undergrads at CWU, there is this kind of gold standard out there. And then in the Caltech training of just world-class science, and the integrity and the values, and the professionalism that goes with science. And you really get that drilled into you at Caltech. I think in my dealings with my undergrads and my grad students, those values and that experiences of kind of gold standard in terms of education, gold standard in terms of scientific training, those inform everything I talk to undergrads about or grad students. I can give you an example. I had a very, very talented grad student from Costa Rica, and she came up, and we were studying these slow slip events, and I was in charge of all the GPS stuff, but she wanted to do seismology. I pulled her out of Otsikori, which is their Seismo lab, when I taught a class down there. And so she came up to do seismology. And I'm like, okay, well, this guy Obara has discovered tremor. Let's start looking at tremor on these events in Cascadia. And I remember at the time thinking, okay, we're going to have a wall between us because we're going to compare what you're doing seismically with what I'm doing geodetically. And this has got to be a double blind. You cannot be seeing what I'm doing, and I cannot be seeing what you're doing. And we ended up and it turns out it was very, very important to keep those blinders up. And that came out of coffee discussions at Caltech about the importance of data that didn't fit your model. And you do not throw that data away. That's the most important data you've got, because it tells you your model's not doing something, right? And it's not explaining something. And so I think I'm mangling the answer here, but somehow between the pure, READ exists to educate students and only educate students. The faculty don't do research, and their tenure, their promotions, all of their criteria are teaching based, which is very different than Caltech. But when I deal with students, I mean, those two voices are in my head at the time, and so it's a very rich. I'm very lucky. My God, as I get older, I realize how incredibly fortunate I was in terms of the training I received.
Yeah. Tim, on that note, for the last part of our talk, a few retrospective questions. We'll end looking to the future. What has stayed with you from your training at Caltech? What informs your approach to the data, the way that you collaborate, your sense of what are the important things to focus on?
There's a whole bunch. What would I start with? I would start with something. I heard both Don Helmberger say this, and I heard Hugh Taylor, who's a geochemist. I think he's passed now. Said he's like, stick to the data. Models come and go, interpretations come and go, but the one thing that doesn't change is the data. Stick to the data. The closer you stay to the data, the safer you'll be. That's always been there. Another one is harder to put words to, but you go through life. Life throws curveballs at you of all kinds. And I would say that, and I've had a few, but the idea of me as a scientist who should be spending most of the time thinking like a scientist about stuff, that's this, it's an attractor that brings me back to who I am. And I think that's a function of Caltech. Totally. I can get interested in something for a while, but eventually I come back to this. I need to be looking at data, thinking about the world like a scientist, expanding this, trying to do that, model this or whatever. And I don't know, I'd probably, if I hadn't gone to Caltech and gone through all that, I'd probably be, chasing money, I suppose. Because I think that make money is probably what fills that void in mission and purpose and cognition for a lot of people. But for me, Caltech, I assume that's how I would have been. I don't know. But for me, it's not about making money. It's science. It's do stuff that's meaningful scientifically. That's maybe limiting. It's not, that doesn't mean I'm doing stuff that's meaningful in terms of stopping world hunger or global peace but stay true to science, stay a scientist, and educate. And increasingly as I grow older, like making sure these students kind of get it, that's incredibly important. That's growing and growing and growing for me. That came, I attribute that entirely to Caltech.
On the note of the science specifically, what were the open questions when you were a graduate student? And among them, what's been resolved and what remains perhaps as open as when you first encountered it 25 years ago?
Well, are earthquakes time predictable or recurrence interval predictable. That was still kind of being bandied around. I think the preponderance of it is no, they're not. And nobody debates that anymore. One thing that hasn't changed, which is infuriating to me, is some of the fine details of these big structural transitions deep in the earth. Transition zone structures, core mantle boundary structures. This is probably going to irritate all kinds of Seismo lab faculty, but the Earth attenuates the high frequencies and it absorbs them, but it's the high frequencies that carry the precise information. In volume 3 of the Feynman lectures, he's got a very beautiful explanation of when the diffracted energy starts to rival the direct energy, you have no resolving power. And he's talking about why with like optical microscopes, you can only see so small and you got to go to electron microscopes. And in seismology, if you're losing the high frequencies, you're losing the detailed statements about the physics ability to resolve detailed structures. And so long as Earth continues to absorb high frequencies and preferentially transmits the lower frequencies, you're never going to have that information. So there are a lot of details about deep structures of the Earth that, I mean, it's infuriating because a year or so ago, I was asked to chair an AGU session on the exact same stuff that Helmberger and I were publishing in the mid-90s, and the discipline hasn't changed. And I'm like, screw this, man. So there are some things like that that are just limited. But I would say the big one is the incredible activity of active faults that aren't currently undergoing big earthquakes, but are doing all kinds of other stuff. That the marching along of technology has allowed us to see. So I'd say those are the big ones.
Finally, Tim, last question, looking to the future, and however long you define a research plan or agenda, 5 years, 10 years, whatever it is, what's left for you to accomplish and how do you get there?
I've actually got a piece of paper on my desk that whenever I have an idea, I write it down, and there's a lot of stuff on that piece of paper. And I would like to pick off 3 or 4 of those things that remain before I retire, and if I might have 15 years left in my career. And a couple of them are fairly meaty things. One of the things I think is really interesting is I don't believe anybody in the greater discipline of seismology has really put these extremely broadband seismometers to use in a way that really squeezes the last drop of energy out of the orange, so to speak. You can combine those measurements with, one of the things I have been working on is to put 360-second corner frequencies. So these are ultra broadband instruments on which you can see solid earth tides, you can see storm fronts come in. Transform those into the ITRF, which is the geodetic reference frame that we use in GPS, and then start looking at some of these slow slip events that we see in Cascadia and see if we can pull out 500,000 second long slip pulses that elude strain meters that are too small for the GPS to see and are so far out of the spectrum that the Struckheisens can see. Typically, unless you orient them in a reference frame, because you can't correlate the signals from station to station. So that's a project that I've actually been chipping away at for the last year or so. This global seismic network that comprises, high rate GNSS receivers around the world. I would really like one of the networks we're positioning now to capture a big earthquake and characterize it in 20 seconds. That would be an affirmation. We did capture the Ridgecrest earthquake in 2019, but that was small. That was a 7.1, I think. But one of these big 8s would be really gratifying.
And that's technologically feasible. It's just a matter of being in the right place at the right time.
Yep. Yeah. We're doing it right now, and all the filters are running. And if we just need the earthquake to happen under a subduction zone where we have access to GPS receivers. and we have 1,800 coming in from around the world. I'm rooting on Chile, Alaska, or New Zealand. So that's kind of where I am. Yeah, it's interesting because I'm now, I'm 2/3 of the way through my career. So you start to look back and you're like, wow, okay, well, I hope I made something of it. So,
Tim, on that note, this has been a terrific conversation. I'm so glad we connected for this. I'd like to thank you so much.
Okay, well, thank you.